So the last speaker of the morning is Gemma de las Cuevas, who is in Innsbruck. It's a pleasure to have her here. And she'll tell us about how it's not just quantum theory that is strange and counterintuitive, and in fact how there's problems in all theories that try to be universal.
All right. Well, thanks a lot, Lydia. I'm not sure, however, that I'm going to address that notion of universality you just kind of referred to. But I'll try to go step by step and try to explain to you why I think universality is interesting and what it means. It's quite difficult, actually, to kind of pin down what it means. But first, let me start by thanking Nuria and Lydia for setting up this summer school. I think it's wonderful. I like everything about it. In particular, I like that it's named after a natural event like the solstice. And in fact, the solstice happened in Zurich, happened today about 10 minutes ago. So it's quite timely indeed. And so I thought that since this is a school, I'll start slowly. And I will just talk about the example of computation. Like, what does universality mean for computation and undecidability in there? Because that's the case we understand best. And so that's going to be like a small crash course into computability theory, which I think is kind of useful for physicists anyway, who have probably not seen that. And later, after lunch, I'll talk about spin models and our attempts to try to relate these to notions of universality, as well as others. All right, so our central actress in computation is a Turing machine. And this is a drawing by Mirte van der Eyden. She's a student in our group, which I like very much. That's definitely not any sort of common drawing of a Turing machine. And I'll try to tell you what it is. So a Turing machine is a model of computation, which consists of a head. So it's abstractly defined, okay? So the head is nothing, I mean, it can be physically instantiated in many ways, okay? And a tape. And the head does something on the tape. And ultimately, the head accepts or rejects whatever input, whatever string of symbols was written on the tape. Well, actually, it could also get stuck in a loop that is not halt. Okay. So let me first of all, perhaps that's one of the most common pictures of a Turing machine. This was drawn by Penrose in his book, The Emperor's New Mind, in '89. But I prefer Mirte's drawing. I think it's clearer. Okay, so let me be a little more precise. So the head has an internal state, which is taken from a finite set of states. So Q is an element of a so-called finite alphabet that I'm calling here gamma. Okay, a finite alphabet is a finite number of symbols for our purposes. Something like 0, 1, or ABC, or if you have a single symbol like a diamond, that's called a unary alphabet. Okay. It's very important that in all of these basic notions of computation, as you're going to see, everything is finite except for the length of the tape. Okay. So I really see Turing machines as a principled way of reaching out to infinity somehow. And from this set of states in the head, there are some distinguished states. One is a starting state, so the initial state of the computation. Another is an accepting state, and another is a rejecting state. Both in the accepting state and in the rejecting state, the Turing machine then halts and concludes, or like the result of that process is that it has accepted or rejected the string. The tape contains symbols also from a finite alphabet. Say R, say a symbol is called R, and it's an element of sigma, some other finite alphabet. It doesn't matter which finite alphabet we pick, so I'm not going to specify what gamma and sigma are. And it also contains a special symbol called a blank symbol, because the initial input of the tape is finite but unbounded. So everything else, let's say, all the cells that are not filled, well, you can imagine them filled with this blank symbol. It's of unbounded length. I don't want to use the word infinite because I'm really afraid of infinity, especially in physics. So let's say unbounded. All right. Now at each step, that's the action, okay? At each step, the head reads a cell of the tape, overwrites it, changes its internal state, and moves left or right. So this is described by the following transition function or transition rule. So we have Q and R. So Q is the state of the head. R is the symbol it's reading currently in the tape. So Q and R are transformed to P, that's another state of the head. S is the overwritten symbol on that cell of the tape, and an action M, which, sorry, not an action, a movement. So it's going to move left or right. So I mean, what the Turing machine does on the input, okay, it does not commute, so to say, like it matters in what order it does it. So it matters whether it moves left or right at each step. It will amount to a different algorithm. And then there's a finite number of such transition rules. Okay, so everything is finite. So you see, finite, but I'm not putting a bound. So this finite could be a ridiculously large number and be finite, okay? But that's how these things are set up in computation. So technically, yeah, I'm going to have a finite number of such transition rules. I can put like a subindex I, and this little I is going to run through some finite set. Everything's finite. Oops, sorry. And the program of the Turing machine is this finite set of transition rules. Okay? I mean, one also needs to specify on what alphabet it is acting, like the alphabet of the tape. But once that convention is fixed, then the program is what the machine does on that string. So it is this finite set of transition rules. Okay, intuitively, a Turing machine is what a human computer, remember computers used to be humans in the 20s, like about 100 years ago, mostly women. So it's what a human computer can do with finite memory. So imagine this woman with a finite memory, finite number of states in her head, and a notebook on which you can write a symbol from a finite alphabet on every page of the notebook. And she can like read a certain symbol from a page of the notebook and then flip the page backwards or forward, and overwrite that symbol. Okay? And okay, I guess Turing was inspired by this idea. So Turing proposed this model of computation, trying to answer the question, what is a computer? Which I think is a really difficult question to answer, especially like it was asked before there were any instantiations of computers, right? And so they had to provide a question, an answer. Actually, they did provide answers, very different answers, which turned out to be all equivalent to each other, remarkably. Okay. Now, this definition is very robust in contrast to others of weaker machines that we will see later. For instance, the following modifications do not change the power. What is the power? The power is the type of languages they accept. I will go there in a minute. Okay, a Turing machine accepts a certain kind of language. It's called a recursively enumerable language. And now the following modifications or like add-ons do not change. Do not change this capability. One can add more tapes. That doesn't make a difference because if you have a finite number of tapes, of course. Because if you have a finite number of tapes, then that's equivalent to having a single tape with an enlarged alphabet, right? Like the alphabet is going to be like the product of each of the alphabets. And finite times finite is finite. You could have the tape being semi-infinite, instead like bounded on one side. That doesn't matter either. You could have a unary tape alphabet. I'm going to define unary in a second. Unary is what you can do when you have a single symbol. You could have access to another Turing machine at every step, like as a subroutine. That doesn't matter either. Okay, that's an important one. You could have non-deterministic rules. And this means that at every step, so remember these transition rules I showed you? imagine that the Turing machine had the capability of going into multiple output states at once. So it had a magical capability of going to both. So exploring two computational paths at once. This is what defines the class, anyway, non-deterministic polynomial time. For polynomial time, I'll mention that later. Okay, so that's a non-deterministic rule. But guess what? These multiple paths can be expressed as deterministic paths on an exponential, or as another finite larger number of deterministic transition rules. So that doesn't matter either. In practice, it's very cumbersome to write algorithms for Turing machines. Okay, so most explanations you'll see are quite high level, kind of saying in words what they actually do, as I will do in a second. They are one of several models of computations. Church came up with lambda calculus, and there are partial recursive functions by Gödel, I guess. Tax systems, there are many others, and some of them look really different on the, like apparently as a system of computation, yet they are equally powerful. This is remarkable, and underlies the Church-Turing thesis, which in words says that a function on the natural numbers can be calculated by an effective method, if and only if it is computable by a Turing machine. So in plain words, this is saying that whatever process of computation can be instantiated in the physical world is captured by the model of computation provided by Turing machines or by the other models of computation. It's worth mentioning that David Deutsch provided a quantum version of this principle, so of this thesis, and argues that he transformed it into a principle in his famous 85 paper. So, but what matters for us is that computable now means Turing computable. Okay, so they capture the notion of effective computability. That's a very elusive notion, right? And that's a concrete model to capture that. Okay, now comes the kind of a great kind of part, a great kind of discovery already by Turing himself, namely the existence of universal Turing machines. Okay, naively one expects that for every function one wants to compute, one needs to build a new Turing machine. Right? Okay, maybe naively, maybe 100 years ago, okay. Not anymore because we are all used to reprogrammable machines these days, but yeah, I would still argue that that's what one would naively expect, but this is not the case. So there is a single program that can run any computation, and that is the universal Turing machine. Let me explain that. So this universal Turing machine has a fixed program, that is to say it has fixed transition rules, but here the key of the argument is that it is fed not only the input, but an enlarged input, let's say, an enlarged piece of data, so that the first part of the data contains a description of the Turing machine that the universal Turing machine needs to simulate. So this is the idea. We had a Turing machine T, and naively, I mean, you expect that it is fed a natural number x, and it either accepts it or rejects it. It's a little more complicated because it might be undefined on that number, but anyway. Now U is fed a description of T and X, and it behaves like, in some possibly encoded way, like T. So this is a reprogrammable machine. The hardware is the program of the universal Turing machine. And the software is the description of the algorithm, which is part of the tape. Okay, let me explain. So the key element here is the fact that the Turing machine can be cast as a string, right? This is the key kind of the key conceptual bit. the most surprising thing that has happened here. And this works as follows. I'll give you one of the many possible ways of casting a Turing machine as a string. So let's encode the program as data. Consider a Turing machine T and fix the head alphabet to be unary. I define this here. So if you have a single symbol, like a diamond, what's the only thing that you can do with it? You can use many copies of this symbol. It's like as if you had like a tally mark. All what you can do is put very many of those and count this way, right? So in particular, the natural number n is encoded as n copies of that symbol. Okay? And this is denoted by diamond to the n. This just means concatenation n times. Okay, identify left with 1 and right with 2. Now that's the key. The transition rule QR goes to PSM is encoded as the following string. We have 1s as separators, and in the middle we will have a number of zeros. And how many zeros encodes P? And how many zeros encodes R? And how? So particularly, we have the string 1, 0 to the P. So these are P zeros, a separator 1, 0 to the R, and then another separator 1, and then 0 to the Q, another separator 1, and 0 to the R, and then 0 to the M. And M was 1 or 2, depending on whether it was supposed to move left or right. So as long as you know what the string means, this string is encoding one transition rule. And multiple transition rules can be encoded by adding an additional 1 between the first transition rule and the second transition rule. So here I would have encoding for the first one an extra 1, encoding for the second one an extra 1, and so on. That's one example. So this string encodes a program. And I will call it d of t for a description of t. Okay, and now we need a universal Turing machine that knows how to read this program and interpret it. And one possibility is the following. So it is input d of t, then a special symbol, like, it's not called hashtag, it's called hash sign, I think. Hashtag is only for Twitter, so. Yeah, hash sign, and then x. And it does the following. So it has 3 tapes. As we mentioned earlier, that's all right. That's allowed, that's innocuous. The top tape contains the description of t. The middle tape initially contains x. So technically, if the top tape contains initially dt hash sign x, then x is copied to the middle tape. All right, so the middle tape initially contains x, and later will hold the simulated contents of this tape. Right, so the middle tape will simulate the tape of t. Remember that u is imitating t, is mimicking t, is behaving like t. Bottom tape will contain the current state of t, that means the state of the head of t, and the position of t's head. Both are finite strings. All right, now u simulates t on input x one step at a time, as you might expect, shuttling back and forth between dt and the simulated contents of t's tape. So it's going to be looking for, so in what state is the head of t right now? Okay, then I'm going to look at the description of t for a transition rule whose head state matches the current one. And then it's going to also look for a transition rule whose symbol on the tape matches the current one. And then it's going to read what goes next. And then it's going to overwrite the tape. And it's going to change the state of the head, and so on. So indeed, in each step, u updates t states and simulated tape contents tape contents as dictated by T's transition rules. And if T ever holds and accepts, or holds and rejects, then U does the same. Okay, as I promised earlier, that's a very high-level description, and this is the one that makes sense, because if I had provided here actual transition rules, they would be very confusing, at least for my mind, and I assume your minds are not computer minds either, so they're hard to read for people, and not particularly insightful. What's insightful is to understand what's going on. Okay, so we have the following situation. As I said earlier, naively, one might have expected that if you wanted to compute the square of a number, you had to build something. If you wanted to compute, I don't know, the prime factors of a number, you had to build something else. This is not the case. It suffices to build a universal Turing machine and then feed the description of what it's supposed to do as part of the input. That's a wonderful idea. Okay, that's I like to imagine this as with Chaplin in modern times. So this is a notion of universality, the notion that there is an object that can simulate any computation. And to my mind, it's the most important or the best understood notion of universality. So conceptually, what's going on here? Well, programs seem to be at a higher hierarchical level than data. But the distinction is only superficial, because programs can be encoded as data, as we saw. And this data tells the machine what program it is supposed to run. So to me, this is like a strange loop or a tangled hierarchy. Of course, this is borrowed by Hofstadter, from Hofstadter and SQuID et Charbach, if you've read it. It's a classic from '79. And this strange loop is found in, for example, Escher's drawings, like in this famous drawing Hands. So we thought that the program was at a higher hierarchical level than the data because the program determined which strings were accepted and which were rejected. But we've learned that actually the data has something to tell to the program, as in how it's supposed to behave. It's hard to make this intuition precise, but something like that is going on. And of course, this is, or at least the drawing and similarity with Escher is borrowed from this fascinating book. And I couldn't resist showing another example of a tangled hierarchy. That's another drawing by Escher, where it isn't clear whether that person is in an exhibit hall or in a coastal village. I think that something like that is going on in universality, at least for computation. Okay, let me say a few words about the languages of machines, namely the languages that machines accept. So first of all, what's a formal language? Formal in contrast to natural. A natural language is Swiss German, or like English, or Chinese, or whatever. A formal language is a lot simpler. It's usually denoted by L, and it is a subset of sigma star, where sigma is a finite alphabet. Now, what's sigma star? It's the clean star of an alphabet, which is defined as the union of the n for any length, n, of the n-fold concatenation, or the n-fold Cartesian product of sigma. In plain words, it is the set of all strings of any length over a finite alphabet. For example, if sigma were 0, 1, then sigma star would be the set of all 0, 1 strings of any length. And now L is just defined as a subset of this huge set. Okay, that's all. Okay, now some languages are harder than others, as we will see in a second. Yeah. Now the set of strings. So what does a Turing machine do? It accepts a bunch of strings. Now the set of strings accepted by a Turing machine is usually denoted L of M. Now, we say that the Turing machine M accepts a language L if for every string in L, M accepts X. Okay, so I'm only talking about these are called the yes instances. So the strings in L are called the instances of L. So when I say that, so I'm not saying anything about the no instances so far here. If additionally, for every string not in L, M rejects X, then we say that M decides the language. So for M to decide the language, it must be able to correctly say which are in and which are out. A language is recursively enumerable if it is accepted by a Turing machine. And it is decidable if it is decided by a Turing machine. Okay, maybe this will help. So the recursively enumerable languages are those which are accepted by some Turing machine. The co-recursively enumerable languages are those which are like whose negation is accepted by a Turing machine, like the complement of that language. So all strings which are not in there. If a language is only recursively enumerable or co-recursively enumerable, you say that it is semi-decidable or undecidable if you're a little less precise. If you're at the intersection, then you are decidable or computable. So in this talk, I will use the two terms indistinguishably, decidable and computable. Okay? That decidable is not the same as recursively enumerable was already shown by Turing. For example, with the halting function, which I will revisit in a second. Let me mention that the polynomially bounded version of this problem is the very famous P not equal MP conjecture, right? Which is, of course, open, and it's a remarkable fact that it is open despite massive efforts for decades in the field and despite the fact that so many other theorems and statements depend on this conjecture being true, and I don't understand why it's so hard to prove. Yeah. Okay, so now I'd like to tell you something. Why do I like languages and why I think this is insightful and why am I saying all of that? Because I think they provide another perspective on the same kind of things that I'm trying to say here. Namely, a language accepted by a Turing machine has a grammar. Now, a grammar here in this talk is just a finite set of production rules. Again, it is a grammar of a formal language, which is a lot easier than a grammar of a natural language, as usual. So we have kind of this dual description. So what characterizes a machine? A program. And what was a program? Remember, it was a finite set of transition rules. That accepts a language. And this language, if it is accepted by a Turing machine, has a grammar. And what is a grammar? It's a finite set of production rules. So both are like infinite sets, or particularly the language is like an infinite set, which has a finite structure, or which admits a finite characterization. And that's a really strong condition, as we will see in a second. It's of measure 0, actually. So you can think both of a program and a grammar as a mold that can be applied an unbounded number of times to reach out to that infinite set. And to illustrate that, let me say a few words about weaker types of machines than Turing machines. So we have seen that Turing machines recognize or accept recursively enumerable languages, which have a grammar which is often called phase structure or unstructured grammar. This is the so-called Chomsky hierarchy of languages, where we have like linear bounded automata, which recognize context-sensitive languages. Now, linear bounded automata are like Turing machines, which can only use a linear amount of tape. They are non-robust to many modifications. Push-down automata are a funny model of computation. They are like a Turing machine that can only move right, cannot overwrite, but has a stack. It's a different kind of stack than the one John was talking about. They have a stack where one can put things like apples and oranges, and then one can pop things off, like oranges and apples. And it's kind of a memory that the Pujan automata has. And they recognize so-called context-free languages, which have a context-free grammar, which is very important, I think. And then there are finite state automata, which recognize regular languages. Finite state automata essentially do pattern recognition. So they are machines that, they are like a push-down automaton without a stack, essentially, yeah.
Are these cellular automatons are called finite state automatons? Like cellular automata is a subset of finite state automatons or in a different class?
I'm not sure. It may depend on the type of cellular automaton you look at. Because some cellular automata, like this famous Rule 110, claims to be Turing complete. So that must mean that you can encode any computation in the input of the cellular automaton. But yeah, I don't know. I mean, one would have to look at that. Yeah. Indeed, in the big book by Stephen Wolfram on a new kind of science, he considers many what seem to be equivalent models of computation. He observes universality in many of those, but he fails to cite kind of well-known sources from the field and to connect his discoveries to well-established literature. Okay, now, there is no universality for these weaker types of automata. And there are many other languages. Like most languages do not have a grammar, are outside of this Chomsky hierarchy. So they are languages not accepted by any physically realizable, I should say, model of computation. I mean, you can come up with imagined models of computation. That's called higher order computation or so. You can play lots of games. That's fun to do. But to the best of our knowledge, we still kind of believe in the Church-Turing thesis or a possibly quantum version of that. So I would still claim that they are not physically realizable. And this may change if we are able to jump into a wormhole or something like that and leave a Turing machine running in the first universe and so on. But yeah, for the moment, they are not physically realizable. So they don't have a grammar. And essentially, every language is in here, okay? Is outside those with a grammar. Having a grammar is really special, at least from a counting perspective. I'll try to explain this in a second. So exactly, let me go to uncomputable functions, which is another way of saying languages without a grammar. A Turing machine computes a function, say, from the naturals to 0, 1, meaning it accepts or rejects the string. This function expresses an attribute, or you can imagine that this function is expressing an attribute. I like this perspective of the natural numbers. That is a property, an attribute, that number may or may not have. It's a binary attribute. And so the output of the function is 1 if that number has the property, and it is 0 if it doesn't. For example, being an odd number, or being a prime number, or being larger than a Google, or, I don't know, being a multiple of 51. Okay, all examples I just mentioned are really simple and have a grammar. But that's just because of the limitations of my mind. Most examples do not have a grammar. Okay, let me go there. Now, every such function f can be identified with, I would call this the extension of the function, with a set of elements where it is true, with a set of elements which have that property. It's like identifying the property of being odd with the set of odd numbers. Now, this is an element of the power set of the naturals. What is the power set? The power set is the set of all subsets of the naturals. So for example, it contains the empty set. It contains all sets with a single element, just 1, just 2, just 3. But it also contains all subsets with 2 elements, 1, 2, 1, 3, 1, 5, 1, 4, 1, 5, and so on. All subsets with 3 elements, all subsets with 4 elements, and so on. But it also contains the subset of all odd numbers. So we would identify the property or the function f with a subset of all odd numbers, which is an element of the power set of the naturals. So you can imagine that the power set of the naturals is like the set of all of its attributes, if you identify attributes with the extension of the attribute. Therefore, there are as many attributes as elements of the power set, 2 to the cardinality of the naturals. On the other hand, a Turing machine can be encoded as a finite string, and finite strings can be identified with the natural numbers. So the number of Turing machines is the cardinality of the naturals. By Cantor's theorem, the cardinality of a set is always smaller than the cardinality of its power set. In particular, the cardinality of the naturals is strictly smaller than the cardinality of its power set. These are different kinds of infinity. They are fundamentally different. So it follows from this simple counting argument that essentially every function is uncomputable. They are different kinds of infinity, as I said. In other words, essentially every attribute has no grammar. So the vast majority of attributes you can imagine are totally crazy. They have no finite description. These examples are rarities, the ones of saying something kind of meaningful or something that you can say in plain words. Most of them are completely crazy subsets of the naturals. Oh, sorry. Yeah, subsets of the naturals are elements of the power set. Another story is what happens to interesting attributes. And that's difficult to answer because it's difficult to quantify interesting. But, well, on the one hand, one could argue that having a grammar or a finite description contributes to the interestingness of a function, right? So I would imagine that interesting is not uniformly distributed. I don't know how it is distributed. Yeah. But actually, I'm just going to give you the most famous example of an interesting yet uncomputable function. And that's the halting function or problem. This is important for historical reasons, and I'm sure you've heard of it. So I'd like to go through the argument and highlight an aspect of that. So this is the following problem. Given the code of a machine d of t and an input x, will t halt on x? Now, this is uncomputable, which is another way of saying that the language consisting of the description of t followed by the input, such that now we write a condition in words which cannot be translated to a finite set of transition rules of a machine, okay? Or to a grammar, okay? Such that t halts on x. So this language is not decidable. Remember that decidable was defined as the intersection of recursively enumerable and co-recursively enumerable. In fact, it's recursively enumerable, but it's not co-recursively enumerable. So technically, it's semi-decidable. Okay, how do you prove it? Very simple. Assume it were computable. So again, it's a proof by contradiction, like Cantor's theorem. So assume there's a machine, M, that accepts every yes instance and rejects every no instance. So that does the job both on the yes and on the no side. Construct a new machine P for paradox, which halts if M does not halt, and which does not halt if M halts. Like you can add a finite kind of transition rule so that if one halts, the other kind of gets stuck in a loop forever, and if one does not halt, the other kind of stops. So that's like negation. I'll be there. I'll come there in a second. Now, feed it its own description. So feed it d of p. So if p is a Turing machine, then it has a description, d of p. And for the second part of the input another valid string must be d of p to p. Now you conclude that p holds if and only if p does not hold on, I should say, d of p. You don't want to accept that contradiction, so you conclude that p cannot exist, and therefore m cannot exist because their existence was tied together. If one exists, the other exists as well, and vice versa. Okay, so what has happened here is a proof by self-reference and negation. In other words, that's the liar paradox. Okay? This is essentially saying, I'm a liar. It's constructing the liar paradox in computability, and the conclusion we've drawn out of that paradox is that a certain object could not exist. So that's how we have escaped the paradox. In other occasions, you escape it differently, or you draw a different conclusion. And we'll have more to say about the liar paradox in the second session. And I think that's all I wanted to say for now. Thanks. Yeah.
One very nice comment Martin made is that he thinks that the duality between programs and the machines is like the Choya-Mikulski in the market.
Not really. So that's something I learned from Toby Reinhardt, who is sitting here. You can see a grammar as an active description of a language because it generates, like the production rules generate the language, whereas the transition rules of a machine are more of a passive description of a language because they are doing something in the head which ultimately determine whether that string is accepted or rejected. It's not like Choya-Mikulski. The mathematical objects are different. It's, I mean, only in a very loose sense. It's some sort of duality, but even duality in a very loose sense. But yeah, thanks for the inspiration. I mean, the Choya-Mikulski thing is a theorem. This is also a theorem, if you want. It's just different.
Someone asked if these other languages are known not to be physically realizable.
What does it mean for a language to be physically realizable? I don't know, because it contains an infinite amount of strings. And to the best of my knowledge and my understanding, infinity is not a physical concept. So I don't even know what it means for a regular language, which is infinite, the simplest kind of language, to be physically realizable. In fact, I don't even know what it means for a string to be physically realizable. I mean, I guess that depends on some identification between information objects, or strings, and physical degrees of freedom.
So this might stem from my limited understanding of your statement on the hierarchy of program and data. So I was just wondering that a universal computer would, I mean, at the end it needs a program, right? Like how it will interpret its inputs. So does that not put program at a higher hierarchy than data?
I'm sorry, I couldn't understand the question. Would you mind repeating the final part?
So I was thinking that a universal computer would need a program in order for it to execute its function, right? So does that not make a program a higher hierarchy than data? Because
I mean, my way of understanding this is that a priori, programs and data are different things, like belong to different categories. Programs accept or reject data, and in this sense, they kind of define the function over data. And so in this sense, I would understand them to be in a higher level than data. But when these programs reach a certain level of expressivity, namely Turing machines, That doesn't happen for weaker kinds of machines. And this distinction is superfluous, is washed out, because programs can be encoded as data, and this data can be fed to a single machine. And so a single machine suffices to talk about or to simulate all of its fellow elements, all other Turing machines. It is weird that that happens. Usually to simulate things in a certain things, you need to be at a higher level than those things. How are you supposed to talk about your fellow element otherwise? I don't know how to express it better. Of course, the trick is that the input of the universal Turing machine is larger. It has like a larger domain. And you use these auxiliary variables to encode, to tell the universal Turing machine how it is supposed to behave. That's an intuition which at least helps me, but I'm sorry if I cannot make it more precise at this point.